else? Okay, in the last class, I think we started with, okay, I'll share my desktop, wait. I think we have started with the second module, which is about okay. So the learning outcomes for this module are, I told you, we'll be able to explain different measures and concepts of errors, describe the different sources of error in engineering analysis and strategies to keep them under control. And the third thing is we should be able to explain the computer representation of numbers and its implication to the round-off error. The last one is articulate the meaning of Taylor series and its significance in numerical analysis. So these are the outcomes. I think we went over. I told you that in engineering analysis, in engineering, no matter whether you're doing measurements or whether you're actually calculating things, there is no such thing as nobody can claim that he has a perfect, exact, and accurate and precise answer. It's not possible. There is always some deviation from the reality, and that reality no one knows. Okay. Now, if you get to that level, you can always say that even a simple thing like what is someone's weight or what is someone's height, whatever number you give, I have to work with the assumption that that is inexact. There is some error in it. Okay, so all answers obtained in engineering have some amount of error. Now, when I say error, what it means is the difference between the answer that you are providing and the actual truth of that number, the true value of that number. That is error. Again, we don't know the true value, and except for cases like in a classroom, for the simple problems that I give you, I may claim that I know the true value. But when you go and go out in the real world and you do experiments, there is no way that you will know what the true value of something is. Okay, if as an engineer, if I'm asking you to measure radius of some component, there's a nut and bolt, I'm asking you to measure the pitch of the thread and things like that. You'll measure, you'll give me a couple of numbers and some digits and all, but there has to be an error in that. You cannot say that your measure is your instrument is so precise that you will get the same number whatever I do. No, that's not the case. Now, this is the value. This is the definition of true error. Again, what is important, I told in the last class, is not the actual value of the error, but the magnitude of the error compared to the magnitude of the true value. Because I told you last week, right? If you're trying to measure something whose magnitude is in microns, if you're trying to measure something that is 10 microns, which is 10 to the negative 6 meters, in that measurement, if you say your error is 10 to the minus 7 meters, that is still a large error because you are making 10% error there. If you look at the error value, you'll say, okay, my error is 0.00000001 meters. But should I be impressed? No, because the value that you're trying to measure is 0.00005. In that context, this error is also very large. Whereas at the same note, if I'm saying that I made an error of 1,000 kilometers, that may not be bad actually, because if I'm trying to measure a very large distance, like distance from here to moon, and making an error of 1,000 kilometers is perfectly all right, because that is a very small percentage error. So what we should be looking at is not the absolute magnitude of the error, but the relative error. What is the value of error in relation to, in proportion to the true value that you're trying to measure? Okay, that right there becomes more important than the actual value of error. Again, this true error and true relative error, they're impossible to find. You will never know, for the simple reason that you will never know the true value of anything. So what do? We do not know the true value. What do? We usually in engineering, what we do is we have an approximate error. And how do you get an approximate error? You get an approximate error by estimating the number using a better method. Okay. The example I gave you in the last class was, if you're measuring weight of something using a spring balance, you want to know how much error the spring balance is making. What would you do? You will go and find a better instrument which has better precision or better accuracy. You repeat the measurement using that experiment, and will that give the true value, the second instrument? No, definitely not, because nobody knows the true value. No, you cannot claim that it is error free. But all you can claim is that the error in that new instrument is less than the error in your instrument. So the second answer you got using the better instrument, you'll call that a best estimate, and that you can use to estimate error in the your original instrument. Okay, so in here you're trying to get a better approximation, and then approximation will be the approximate error in the solution is going to be what is the best estimate that you got for the answer minus what is the original estimate. That difference will tell you the approximate error, and once again what is more important is the relative estimate, relative approximate error. Then then this the immediate next concern is, how do you get this best estimate? I told you, if you are doing experiments, you have to get a better instrument than what you have, and if you're doing computations, you have to make sure that your numerical error is less somehow. Use a better mathematical model or use a better numerical approach. Somehow you have to improve the model and get a better estimate, and then the difference between the better estimate that you got and the original estimate will tell you what is the approximate value of error that you have in the problem. Okay. Then we had discussed about significant figures. I told you, whenever you give a number uh, in a solution, it doesn't add any new information or any confidence. When you say answer to the question is 1.345689, okay, what does that mean? Are all those really significant numbers? Are you sure that it is 1.567849? Not, are you confident about all those digits? Typically the answer is not. You can confidently say that, for example, okay, so you could say that, for example, I'm asking you what is your velocity, let's say. Okay, then you say, okay, I started from Madanapalli, I came here, and that is 10.4 kilometers, and then you have a stopwatch, let's say. You measured the time you measured in a stop clock, you got the time to be I'll make up some number here, some 3485.68 seconds. Okay, if you do this, if you do that calculation, I'll do it here with the calculator I have in my hand. Give me a second. So, I just made up numbers, right? 10.4 divided by 3685.68. That is sort of answer your, that is sort of a time that your stopwatch will give. Now you got this to be 0.00282. Now, if I look at the calculator, it's giving all these numbers: 2173167 502. Okay, Now the answer, the question is, really, are they all significant? Am I sure, will it not be much better to say that, okay, I know that the velocity is 0.028 and I don't know what other digits are. There's no significant digit beyond that. This is much more reasonable, right? Because are we sure that we know this precisely based on these measurements? Can you claim that you know this velocity that precisely? No. Okay. So generally the rule of thumb is, you know what is the significant digits in your numbers that are going in. These are measurements. So the answer should not, even if you assume that all these 6 digits are significant, then you can only claim that only 1, 2, 3, 4, only at most you can claim that these are significant digits. And these, yes, the calculator is giving them, but we don't know to that significance. Okay, so that is the meaning of significant figures. Significant figure means, real numbers like the one I'm showing here can have many digits before and after the decimal point. But in actual engineering, we should know how many of those are significant, meaning how many of those you can use with confidence, or you can state with confidence that the answer, these digits are correct. And the rest of them, there may be error in that, but these digits are definitely correct. Okay, how many other digits you can say that for sure? That's called significant digits. For example, if I measure distance between Madanapalli and Angallu, if I say 10.4, I have an instrument and I only have 3 significant digits in that instrument. But if I have a better instrument, I may say 2.43, and I say, okay, I'm pretty sure about this digit also. And if you have a more precise instrument, you can say 10.4365. And if your instrument is that accurate, then you'll claim that, okay, all these 6 digits are significant. Measuring time is relatively easier. So you know that, I think, when you measure with a stopwatch, time and all, typically, I think it goes to 0.01 second precision. Okay. Now, so that is a story about significant digits. Again, anyway, this is a repetition. I told you that for instruments, for analog instruments like this, we take the significant digits to be whatever the actual grading on the scale, and because we can kind of estimate between the gradings, you can add one more digit. Here I told you, for example, here I told you that 1, 2, 3, 4, 5, 6, 6. We have 6 actual digits in the meter, and when it rotates, you can kind of estimate, right? Because now you'll say, no, this is 8. The number here is 8, 7, 3, 2, 4. The last digit is not, it's more than 4 and less than 5. So you can estimate kind of saying it's 4.5. And this 5 can also be taken as significant digit, it's allowed. So this here, generally for a general rule for any instrument is, analog instruments like this, whatever you can directly read from the dial plus one estimated digit is the number of significant digits in that measurement. And I think I did not get into the discussion on significant digit arithmetic and all. Maybe I will do that later. But that is the story of significant figures. Now, I'll talk about computer roundoff, in a second here. But we'll move on and we'll discuss about precision and accuracy. And before I go there, any questions on significant digits, true error, true relative error, approximate error, relative approximate error, and significant figures? Any questions on those ideas? So how many students do we have in attendance today? One. Okay. Okay, so I assume, will not waste time. Let us say you all understood whatever was covered in the last class. Now, precision and accuracy. See, I think we talked about precision of an answer or accuracy of an answer in context of engineering or in context of errors. But when an instrument or when a measurement or when a calculation has an error, it could be, we can distinguish between whether it is because of imprecision or whether inaccuracy. I'll tell you what I mean. Okay, so accuracy is the measure of, when the error, there's always errors, right? So accuracy is the measure of how close the calculated value or measured value is to the true value. Okay, that sounds like a standard definition of error. Okay, so if there is no error, then you call accuracy is good. If the error is very small, then you say accuracy is good. If the error in answer is large, then you say the accuracy is not adequate. The accuracy is less. Now, precision is another thing. Now, precision is, a lot of times when you have an answer, it also is associated with uncertainty. For example, um, you did the problem, we did in the first module, we did the problem on the bungee jumper. In that computation, we used mass of the person as a parameter. And also we used the drag coefficient of the man is a parameter. So how do we know that those are true values? They're not. So there is going to be some uncertainty in them. Okay, that body's mass could be 100%, 100 grams here or there, or 500 grams. Typically, you may plus or minus 0.5 kilos error in estimating the weight or mass of a person. Also, the drag coefficient, we get it from correlations. There may be some 5% error in it. So now, in your error, whenever you are reporting an answer, you should say, okay, my answer is after 10 seconds, the bungee jumper is going to have a velocity of 40 meters per second, plus or minus 3 meters per second. So what you're telling is, it could be anywhere between 3 meters per, 47 meters per second and 53 meters per second. For example, you say you give an answer, you'll say, 49 plus or minus 3 meters per second. And that is your imprecision. If this is very small, then you have a precise answer. If this is large, then you have an imprecise answer. But you have to understand that you yourself, when you measure something or when you calculate something, just based on the limitations of your model or just based on the limitations of your measurement, you already know that the answer is imprecise, that there is some variability that you could expect in the answer that you provide. If the variability is very less, then you say good precision. If the variability is very large, then you say bad precision or imprecision is high. Okay. Now that is the story with precision, because all answers have some level of variability. It could be because of data uncertainty. It could be because of uh, you know the imprecision of the instrument that you're using, whatever. Okay, inaccuracy is opposite of accuracy, which means bias. See, if there is a systemic error, I'll tell you, I think I'll show you a figure, you'll get. Inaccuracy is, even with this, this is imprecision. You're saying that 49 plus or minus 3. So there is some imprecision, but if this, even with this imprecision, if it is still away from the true value, then we say your method or your instrument has a bias. Okay. Then the second thing is imprecision. Imprecision is known as uncertainty. I told you is the scatter of the approximate value. Scatter. How far it scatters. We're saying that it's 40, but it could be anywhere between 46 and 52. Somewhere in between. And I'm saying, and I'm claiming that it will be in this number. Okay, so you're being humble and you're telling, okay, I have an answer, but there is some imprecision. There may be in this region, but how is this region compares with the true value? That is the measure of inaccuracy. At least in average, when I say 49, the answer should be close to here, right? For example, you say that you have a method, you say the answer is 49 plus or minus 0.5. Okay, that is very impressive. The precision is correct. The precision is very right. It's very good. But what if the answer is 54? Then your answer is precise, but it's not accurate. It has a bias. It has an it's underestimating grossly. Okay. Another story is if you say you have answer is 49 plus or minus 10. So you're giving me an imprecise answer. If the true value is 50, then very good. Your answer is accurate because with all this scatter, the average is very close to the true value. But you're not able to give it to me precisely. Okay, because every time I ask you, it could be 49 plus or minus 10 is what you're telling. Okay, so see, there's a distinction between accuracy and precision, and this is what you can look at it. For example, uh, you you have a solution, low precision solution, a solution like this, 49 plus or minus 10. So every time I ask you, you say this could be this, this, a lot of scatter you have. Okay, and if I take average of that also, I am way off the mark. Okay, so the fact that even the average of all these scattered numbers is away from the true value, that is called bias or inaccuracy. Okay, okay, this is bias. The fact that in another case, here also the answers have, I'm telling you, it's like a bullseye thing. This is one standard visualization we do to understand the difference between accuracy and precision. Okay, let's say finding a true value is like hitting the bullseye. If you play this dart game or shooting game, this is the bullseye. You're trying to go for it. Okay, and there is one kind of a shooter. He's scattering the bullets all over, and even if you take an average of all that scatter, his aim is not, he has a bias. His aim is little bit off from the target. This is an analogy. What I'm saying is, finding an answer is also like that. You're giving a range of answers, but even if you take an average of that, it's not close to what it is. Alternatively, this is a second type of shooter, let's say. So this person, he cannot consistently shoot at a point, but if you take an average of all his shots, he is on the dot. Okay, he doesn't have a bias. It's not like he's always shooting to the left or shooting to the right, shooting to above the target or below the target. He has no bias towards any one side of the target, but his precision is also poor. Now think of this case. No, this shooter is a very precise shooter. He's always shooting in a very close proximity. There's no scatter. But the problem is he has a bias. His aim is his aim has a bias. Okay, inaccurate aim. He cannot manage to hit the bullseye, but wherever he's hitting, he's consistently hitting there. He's precisely hitting in that region, but somehow he's not able to make it to the bullseye. So he has a bias. And this is a perfect way where this is both precise and accurate. Here the scatter is less and also there is no bias. Okay, so here's the thing. You can think of accuracy and bias are two independent dimensions of error. Okay, so you have error when in both cases. If precision is low, you have error. If accuracy is low, you have error. See, these two cases, accuracy is low and you have errors because that error is mostly because of bias. When precision is low, in these two cases you have error, but here the error is due to error is mostly due to the scatter. We are not getting a good precise answer. Okay, so high precision, high accuracy is what is desired. Okay, but somehow sometimes you cannot avoid this. Even see, look at this. Some person or some method is able to generate very tight results. For example, like this one example I was telling you, you're able to tell that the velocity is 49.05. Your method says this, but the true value is 55. Even though the imprecision in your method is small, the method has a bias. It has the tendency to give a lower estimate for the velocity. Any questions here? Anyone? Okay. Now, at the beginning of next class, I'll ask questions on precision and accuracy. Okay. Accuracy is the measure of how close the calculated measure value, at least in an average. Okay. See, here I think I'll start with the precision. Precision is the measure of how close different measurements or calculations for the same quantity are to each other. Okay. Whenever you do a measurement, for example, even if I go back to the example here, the significant digits, see odometer. Okay, so one way of saying that is if you have this one 87324 and you'll say 0.5 plus or minus 1 or plus or minus 0.5. Using this instrument, you can say that this is your reading and there may be an error of 0.5 kilometers. That's what you can say here, right? So if it turns out that the true value is this, exactly this, then you have a very precise and very accurate answer. But let's say this is quite precise because in this many digits you're saying plus or minus 0.5, it's not a big error. But if the answer turns out to be 8732 6.8, okay, 8732 6.8, then there is a bias. See, this error is not because of the imprecision. It's not because of you not being able to read it precisely. It is because of there actually is a bias to the instrument. The instrument actually is inaccurate. Okay, but the fact that it has limited digits doesn't have anything to do with it, because even the digits it's reading precisely are wrong here. If the true value is this, okay. Do you understand what is the difference between precision and accuracy? Anyone? Okay. Okay. I think we'll move on, but again, I'll ask you questions in the next class. Now, okay, I told you about errors in general. I didn't make a distinction between whether the error is in a computed solution or whether the error is in a measured solution. Whatever I told you so far regarding true error, approximate error, true relative error, approximate relative error, significant figures, and also accuracy and precision. all these terms, they apply to engineering in general, irrespective of whether we are talking about the numbers obtained by measurements or numbers obtained from calculations. What I'll do now is we'll concentrate on errors in computations in engineering analysis. Now, what happens when you do computations? Why do we get errors in computations? Okay, the numerical errors in computations. I'll tell you. Now, numerical errors, again, in engineering analysis, there are two types of error, model errors and numerical errors. I'll talk about numerical errors. Numerical errors is errors that enter the solution that are introduced by numerical computations. I'll tell you what that means. Numerical computations. Okay. In the last module, when we did this problem of dv dt equals g minus cd over m v square. Okay. And I have solved it numerically. When I said solve it numerically, the numerical solution is v at any time t plus delta t equals v at previous time plus delta t times g minus cd over m v square. I told you this is a numerical solution. So instead of solving this analytically, if I solve numerically, I get this solution. So solutions like this, when by choosing to solve it using a numerical method, you are causing an introduction of errors into the solution. When you do this, you automatically know that okay, I'm opening doors for some error to creep up into my solution. So why? So I'll tell you why. No, by solving it this way, this is called a numerical solution. This introduces more errors. I'll tell you why. The first reason for introduction of solutions into numerical methods is because of truncation errors. And we'll talk more about it today. These truncation errors, these are the errors which arise from the fact that numerical methods solve an approximation of the actual model equations. Okay, so this is the actual model equation, whereas you have approximated it. You said, okay, if I approximate dv dt as v at t plus delta t minus v at t divided by delta t. So the approximation you used is, instead of dv dt, you substituted with v at t plus delta t minus v at t divided with delta t. So this approximation you have used there. And because instead of the actual derivative, you are using this numerical derivative, that of course is an approximation, and you're solving an approximate equation, not the actual equation. So the solution to this approximate equation is going to be a little bit different than the solution to that exact equation. And that difference is called truncation error. And how can we estimate this truncation error? Now, what helps us in estimating this truncation error is the Taylor series, which we learn about a little bit in this class. Okay, that is one. The second thing where we can get errors is round off errors, because whenever we are adding multiple terms, the computer has, and again we'll talk about this in today's class. Now, in computers where we only store limited number of digits in the computer. And what that means is, whenever you have to store a number, the real numbers, right? If you have to store a number 1 by 3, okay, the exact value is 1.33333, and it goes to infinity. But when you store it in a computer, it has to be stored like this, right? 0.3333, and you have to stop somewhere. Okay, so this number and this number, because you have truncated, you have rounded off to a limited number of digits, that introduces an error. Those errors, again, we have to be mindful of these errors. We have to be mindful of the fact that when we are solving in a calculator or in a computer, the real numbers are being rounded off to the because we only have a limited number of digits, they are being rounded off, and that introduces an error, and we have to be mindful of that as well. Okay, those are the roundup errors. The third thing is, I think you'll understand this better when we do more problems. But these errors are called convergence errors. Sometimes we solve problems iteratively. This come into picture in iterative solutions. And I'll tell you what an iterative solution is. These come into picture if you don't iterate the solution long enough. These arise from the fact that many methods are solved by iteratively improving the solution, and the convergence is never complete. Okay, if you keep on iterating, eventually you'll get a very accurate error, but you cannot continuously do that, right? You have to stop at some time. So because you stop at some time, it may not have gotten absolute convergence. Again, we'll talk about it. No, what does this mean? There is from the fact that methods are solved by iteratively improving the function, the solution. So what happens here is, I think probably you have studied bisection method and things like that somewhere. Anyway, I'll tell you what this is, iterative solution, and what is the convergence error. But again, these three, they are different from model errors. See, these three are not because of your model equations being wrong, or there are a completely different set of errors that come into the answers because of errors in the model. Here, even if you have a perfect equation, okay, let's say this is your perfect equation, it perfectly exactly represents the reality, the real physics of the problem. Even then, even if there is nothing wrong with the model itself, just by the fact that we are solving this model equation using a numerical method, just because we are using a computer to solve it, even if the equation itself is correct, even if G is correct, CD is correct, everything is correct, because of the approximate method we are using, because of the rounding off in the computer, because of the insufficient convergence, there are going to be errors in the numerical solution. So that's why we call this, these three we are calling them numerical errors, because they have nothing to do with errors in the model. We'll talk about those errors later. Okay, any questions here? Anything? Okay, you're being extremely quiet. I don't know what to do. Okay, so moving on. I think okay. Don't forget about the questions, but let me ask one of you a general thing. Have you come across Taylor series in mathematics before? Anyone? Okay. I think let me take someone's name and ask it to a specific person. No, not this one. Okay, so who do we have here? Pawan Kumar. Pawan Kumar K. Pawan Kumar.
Hello.
Yes, Pawan. Have you come across Taylor series earlier in any math class?
Yeah, yes, sir.
Which class is that?
Um, linear algebra and complex series.
You got, I think you have come across Taylor series in linear algebra class, is it? Anyway,
Yes,
no,
sir.
I asked this because if you already seen it, I can really quickly go through it. Anyway, I'll show it to you and we'll go on from there. Okay, so the next slide has a Taylor series. The reason we're studying Taylor series now is because it has a lot of implication to the numerical methods and numerical errors. Okay, so Taylor series is an infinite series which gives the value of any function at a point in terms of a function value and its derivatives at some base point. Okay, in its, there are many ways to write the Taylor series, but one way I'll tell you, which I like, is like this: function at any point x, or let me say a plus h, okay, and we'll call this base point, and this is some point. Okay, see, so you want to evaluate the value of function at a point which is h away, some distance away from the base point. How you can do it is, you get the function value at the base point plus f prime, the derivative of the function at the base value, divided by the distance between the base point and the second point, divided by 1 factorial, plus h square divided by 2 factorial, the second derivative evaluated at base point, plus h cubed divided by 3 factorial, third derivative of function evaluated at base point, plus again 4 factorial, and the fourth derivative evaluated at base point, and so on and so forth. The nth term is going to be h raised to n divided by n factorial, and nth derivative of the function evaluated at base point. Okay, so have you seen that before? In some other form maybe. So basically, what this series has is, you are trying to find the, x, a plus h, some location, some x. See, you know the function value, let's say function value of a, and the first derivative at a, base point a. Oh, okay, so there's a, let's say there's a base point a, we know function value at that a, plus first derivative, second derivative, and all those things that you know. Then you can find out function value at another point which is h units away from the base point. You can find those in terms of the function value and derivative values. Okay, that is the meaning of Taylor series. Here's another form. The same thing. Instead of a, I gave you x. Instead of h, I wrote delta x. So if you want to find the value of a function at a distance delta x from a point, then you can say the function value at that original point plus the distance divided by 1 factorial times the derivative of the function with respect to x at the base point. That is important. Then distance square by divided by 2 factorial times the function, the second derivative of the function with respect to dx evaluated at the base point. See, all this function and derivatives are evaluated at, all functions and values and derivatives are evaluated at base point x. Okay, and further, this is just delta x square. This is just a polynomial. So usually this gives a polynomial. Okay, I have another example in the next slide. I'll show it to you. Another way to write it is, it can be written in different notations. So the one I wrote in the top is one notation. Now no, the one I have actually typed into the presentation. This is a second notation. They're all identical. It's just we are choosing it in a different way. See, this I said function at any new point will be equal to function at the old point times the distance between the 2 points. See, instead of delta x, I'm writing xi plus 1 minus xi. So basically what happens is xi plus 1, uh, no, x I plus 1 is equal to xi plus delta x. Okay. If I manipulate this, if I substitute this here, instead of x plus delta x, I have xi plus 1. Instead of x, I have xi. And instead of delta x, I have xi plus 1 minus xi. Okay. With that kind of switching of notation, same thing, okay. Function at a point away from the base point will be equal to function at the base point plus the distance between the base point and the second point divided by 1 factorial times the first derivative of the function evaluated at the base point. Now, square of the distance plus, okay, square of the distance between the base point and the second point divided by 2 factorial times the second derivative of the function with respect to x evaluated at the base point. So likewise, third derivative and the derivative and should go all the way to the infinity. If you take all the infinite terms, this in fact is an exact equation. The problem comes when you truncate it to a shorter, series. You can cut anywhere you want. That's called truncation. So if you're saying that I'm neglecting all this, then the fact that you have neglected all this has introduced some error into the method, and that error is called a truncation error. Okay. Any questions on Taylor series here before we move on to the next topic? Actually, I'll show you an example of the Taylor series. Any questions here?
Sorry. Hello, sir.
Yes, please.
Sir, could you say it again? The different notations example. It's quite confusing to listen.
Okay. Who is this?
Sir, Pawan, sir.
Okay, thank you, Pawan. We'll go back and I'll do it again. 1 second. Okay, so I don't know how to make it go away. Oh, I think I know. Okay, 1 second. Okay, see, you see it here. No, first notation I told you was, I gave you the fact. No, I told you that. Let's say you have function. I think in the next slide I have an example. You'll understand it better. But let us say for a given function, you want to approximate it with a polynomial, and you know the function value at some point, and the derivative at that point, and the second derivative at that point, third derivative, fourth derivative, all the way. Let's say you have all the derivatives for that function. And then you want to find the function value at another different point, which is away from the base point. The distance between the new point and the base point is h. So I'm saying I want to know what the function value will be at a point a plus h. And remember, I know function value and all the derivative values at a. So that, I think, what Taylor series says. I think if you if you have studied central value theorem, this can be derived from central value theorem, central limit theorem. Okay, who is that? I think someone might want to mute their mic. I'll do that myself. No, not this one. Okay, okay. I think the problem solved itself. We'll go back. Okay, so if you want to evaluate the function value at some point a plus h, so you take function value at h plus the h, which is the distance between the base point and their second point where you want to evaluate the function, divided by h factorial, 1 factorial times first derivative function. Next, second derivative of the function evaluated at the base point times h square by 2 factorial. Third derivative evaluated at the base point times h cubed over 3 factorial. Likewise, it goes on, and the nth term in Taylor series will be equal to h, the distance raised to nth power, divided by n factorial times the nth derivative of that function evaluated at the base point. Okay, this is one notation. Now, starting from this notation, I made this little modification here. I say instead of a, let's call it point x. Instead of distance h, let me call delta x. Okay, that is the only notation change I did between this one and this one. No, only that. See, wherever there is h, there is delta x, and wherever there is a, there is x. And another notation change I did is, sometimes we do is df dx can be written as f prime of x. I think this is one notation we have for the derivative, right? You have seen this before. F prime could also mean derivative. 2 primes is second derivative. 3 primes is third derivative. 4 primes is fourth derivative, and all the way n primes is equal to nth derivative. So only these modifications I have done, and we got a different notation. And the third notation here comes from the fact that, whenever we do, I think you have seen this when we did the solution for the bungee jumper problem. We have a grid. We say we want to find x values at these points, x1, x2, some particular x locations, xi and xi plus 1. And the distance between consecutive grid points is called delta x. Okay, so in situations like that, so we want to find out value at xi plus 1. So again, same thing, instead of a, the base point, you take it as xi. Okay, and a plus h, the second point, we are calling it as xi plus 1. In other words, h will become, I don't know why this is being so weird like this. Okay, in other words, this is going to be, h is going to be like xi plus 1 minus xi. Okay, see, same equation, these things, these differences, wherever there is a, wherever there is a, xi has come in there, and wherever there was a plus h, we got xi plus 1, and wherever there was h, we have the distance between the 2 points, xi plus 1 minus xi. See, h is here, right? That was h, and instead of h we have that h square is here and h cubed is here. Okay, but it is the same thing. Okay, both of all three different forms are, under different scenarios we use different things. Okay, no, I don't have much time. Hope that answers your question, Pawan. Can we move on? Okay. Uh, I don't know. Okay. When all terms are included, the series gives the exact value, but errors creep in when series is truncated. And that is what we call as truncation error in numerical methods. So I'll give you an example. A Taylor series example. Well, let us take the example of sine of x. Okay, uh, and we'll let us take a base point of, let us say base point is 0. Okay, so fx, let it be equal to sine x. We want to find sine x, so sine x is going to be sine, no, because we want f of x, right? So basically I said base point equal to 0, so which means, you can think of it as you're trying to find f of 0 plus x. Okay, so f of 0 plus x is going to be equal to f of 0 plus x divided by 1 factorial f prime of 0 plus x square divided by 2 factorial f double prime of 0 plus x cubed over 3 factorial f third prime 0, so on and so forth to the infinity. Okay, so this expression we'll use, and we'll try to see what we will get for f of x. Okay, if I say f of x is sine of x, what is f prime of x? Now, what is derivative of sine of x? Anyone? Anyone? That is cosine of x. And f double prime of x is derivative of that. That is negative sine x. F triple prime of x is derivative of this, which is negative cosine x. Yes, please. F of x is sine x z. Okay, and f 4 prime will be equal to negative. No, I think again it will become sine x. Okay, now I want it at a equal to 0. So what we are looking for is at x equal to 0 at base point. F prime of 0, f of 0 equals to 1, no, 0, sine of x. F prime of x is going to be cosine of 0, 1, and this is 0 minus 1, and again this becomes 0, and then the pattern goes on. So at x equal to 0, we know first derivative is 1, second derivative is 0, third derivative is negative 1, fourth derivative is 0, fifth derivative again is positive 1, sixth derivative will be 0. The pattern continues. I'll show you what it means. Okay, so again, I'm with function at a plus x, and here I'm taking a equal to 0, so it's a f at x equals to f at 0 plus x prime. This is called Maclaurin series. When you evaluate the series around the base point of 0, it's called Maclaurin series. And now I want to finish it and take it. Bear with me on 1 second. So f of x is going to be sine x. Df dx is, the first derivative is cosine x. Second derivative is negative sine x. Third derivative is negative cosine x. Fourth derivative is sine x, and so on and so forth. The derivatives you can do. So, if you evaluate all this for the base point of a equal to 0, you will get function value is 0, first derivative is 1, second derivative is 0, third derivative is negative 1. It goes on like that. And if you look at the pattern, if I substitute all these function values back into the series, f of 0 is 0, 1, 0, negative 1, 0, 1, 0, negative 1. That pattern continues. And if you get rid of all the zeros, this will be gone, this will be gone, this will be gone, all the even powers will be gone, only odd powers will stay, which are these: x by 1 factorial, x3 by 3 factorial, x5 by 5 factorial, and the signs are alternating. If you look at, this is what the nth term in the series will look like. Okay, this is called sine series for Taylor series for sine using Maclaurin series. So this You can cut off anywhere. For example, you can truncate it here. So you are getting, what you are getting is a polynomial expression, a polynomial approximation for sine function. You could say sine of x equals x plus or x minus x cubed by 3 plus x to the 5 over 5 factorial. Okay, and this is an expression, by the way. We are approximating. We are saying that sine function is also a polynomial, but it is a truncated polynomial. We are only taking the first 3 terms in the series. So yes, it is a polynomial, but it's an approximation and it has an error. The error is this. We have neglected all this. So that is a truncation error in the series. Okay, I'll stop it there and I'll get the attendance. In the meantime, you can ask questions if you have. Okay, now please answer your attendance. Today is 10th September. Okay, so what is the, I think 360, is 360 here today? Okay, 360 is absent. Anybody in 60 series? Please tell your numbers.
Sir, 363, sir.
63. And then?
3.
Please, anyone else? Okay. Let me turn off the...
364, sir. 364.
I got it. 63, 64. Yes, anyone else in 60 series?